Welcome to the presentation of our paper titled BROFY Toward Essential Integrity Protection for Microservices. My name is Ardhi and I'm with Christof Fetzer, part of the System Engineering Group at TU Dresden. With the introduction of microservices, maintaining trust on a remote service has become more complex. Undoubtedly, the integrity of a microservice is an important aspect of the trust itself. Suppose that you have this service which contains a few of microservices, and then if the trust of, or specifically integrity of service A is now compromised, it will be propagated to other services, in this case service B and C, which eventually make the trust of the overall service now violated. The current state of the art still doesn't completely solve this problem. We have state machine replication, for example, Byzantine fault tolerance, which can help verifying the integrity. However, it introduced extra effort and some extra component need to be implemented as well. And we also need to consider that an adversary can also control the majority or control the replicas and can even break into our service and alter the program. Using TE for protecting integrity, such as using Intel SGX, is pretty straightforward. It covers code and its memory, and it prevents outside access, especially in this case. However, there are two problems in this approach. First, it assumes CPU to be correct, which is not always the case. It's shown by our experiment, which is inspired by Thunderbolt attack. And then there are the second problem that Intel SGX framework is quite tedious to implement, because you have to explicitly implement the trusted region. In this example, we show that not even basic integrity, which only ensures CPU and memory, can be ensured in a microservice. So in our paper, we discussed that issue. Before we are going to answer the previous problem, how are we going now? We use software-based fault tolerance to prevent CPU bit flips. Software fault tolerance work by either by duplicating process, dedicated work on a thread, or duplicating instruction. We pick half because it is simple for both implementation and concept, has next to no requirements except for recovery, which use Intel TSX, and it also supports multi-threading out of the box. And for answering the second problem, so we will use Intel SGX as our TE. Intel SGX is a hardware support for protecting trusted code. It has isolated trusted region called enclave, which prevent untrusted access and give us memory integrity protection out of the box. And this feature also comes with most of the modern CPU in current market. Because the implementing stuff in SGX is quite tedious, we use Scone as our framework. So Scone is a framework to run application inside an SGX enclave. It is a trusted C standard library which has containerized approach, and it supports multiple languages. Scone also has some additional features regarding security and trusted computing in general. We developed BROFY, which in layman terms combining Half and Scone, with the goal of protecting integrity by preventing bit flips from both natural occurrence and all-powerful adversary. And we have a few of assumptions. First is we only have an interest how to prevent integrity violation. So crash is okay because it can be handled externally, and recoverability is a bonus point which will depend on the program itself. And we have desired several features such as it must be container-based approach because we will work on a microservice base. It must have multi-language compatible and has no or few dependencies, and hassle-free implementation for both developers and end users, and support unmodified source code. We also assume the same threat model as Cone, which is a kind of superset of an SGX threat model, which typically has a powerful adversary that has full control of the system and has any privilege level as well. In this slide, you can see how BROFY works on the right side of the slide. Our rationale is as follows. Well, we want to prevent bit flips either by natural occurrence or by some adversary on the CPU by using Half, and on the memory by using SGX. On the SGX, it will protect the integrity of the PRM region, which is processor reserved memory on the SGX, and it also has some integrity tree, which we will discuss later on. So the BROFY design is basically is a LLVM pass that in the end it will be merged with a SCON toolchain. We first re-implement half as a LLVM pass toward Muscle because SCON uses Muscle as its backend. And since there are some changes in the internals, specifically we changed some of the intrinsics so that the pass can see some of our function in the LLVM. We shape our version of LLVM. After the whole LLVM framework has been compiled, then we can compile the actual pass, which is it depends on what features that you want to enable. After that, we adjust front-end compilation so that it compiles based on our rules. For example, maybe we want to enable the FPIC, which is position independent code, and then we also want to statically compile non-libc library because we also want to protect the external libraries that being used by the program as well. After we get the generated object files, which is in this case .o, we will link that object file with SCON libc, which is a SCON runtime, and in the end, symbols from the program will be resolved in the SCON runtime, which makes the program can run on top of the SGX enclave. So we support multiple languages, and then, for example, Python and Rust. However, those two are being done in a different approach. In Python, for example, we need to compile the world interpreter, and then some modules also need to be compiled as well to Muscle. In Rust, we don't need to compile the actual compiler set. We only need to compile the program using Rustc and Cargo to bitcode, and then we will process that bitcode to the rest of our toolchain. What could possibly happen if we have CPU bit flips? First, it will be detected by half. It may or may not immediately recover because it depends on what feature that we have. If it's not recovered, then the program will exit, and of course, the administrator can always restart the program or investigate what is the cause of the bit flips. If we have memory bit flip, well, we expect ECC in the memory to detect that as a first layer because it's quite common nowadays. And if somehow it's breaking through the first layer, then the memory encryption engine in SGX will find the inconsistency between the encrypted memory and the integrity tree. And then if somehow it is inconsistent, then SGX will lock down the whole CPU. So what happened underneath? For example, we have this multiplication function. It will call some instructions such as mul in this case, and then instructions are now will be duplicated in binary level in the file. So there are two multiplication that the results will be compared against, and then those instructions will be executed and will be compared inside an enclave. If somehow the computation are now different, then it bails out. Well, it depends. If you want to recover, then you have to retry it again. And also, if you're talking about the memory, every time you store data on the encrypted memory, you also put something on the integrity tree. When you try to load it, then you have to also compare it to the one in the integrity tree. If somehow the comparison is mismatched, then the SGX will lock down the CPU, and otherwise it's just life goes on as usual. After we implement the toolchain, we want to measure the program's performance compiled by our toolchain with this tool. We run the evaluation on the Intel Xeon machine with 6 cores with 32 GB of RAM, and we also tested multi-threading compute intensive program, which shown on the left side, and also HTTP server in multiple languages such as C, Python, and Rust, and also complex application, in this case represented by Redis and Memcache. On the left side, you can see that our worst case, which is a compute-intensive program, which the runtime of BROFY is actually 1.84 times longer than the native execution. Why this is worst case? Because many of the duplicated instruction is now executed and being compared. If we try to compare that with the average case, like on the right side, the duplicate instruction may have to wait or waiting for I/O or context switch, which the work is not as much as the compute intensive one. Coming back to the right side, we have Redis, which give us the overhead of 28%. And this is pretty average because in our other experiments, the result is between 3 and 37% of overhead. We set a fixed connection number to the server and increase the throughput step by step. And then after that, we can see how many latencies that occur in between that operation. Also, we try to compare on multiple languages. For example, on the left side, you can see Rust on 4 threads, and right side is on 1 thread. So in this case, you want to compare the multi-threading versus single threading. So it is shown that in the single threading, it is actually occurs more overhead than the one in the multi-threading. And this phenomenon is also happens in other languages as well. Regarding the bit flip protection, we underfold the actual CPU to trigger bit flips. We underfold it to minus 256 millivolt on that specific frequency, which is 2.2 gigahertz on a few program variants, like shown on the table. And then we increase the number of retries. We also modify the timeout on how long should we wait before we can assume that there is no fault in this case. And in the end, the takeaway is that, as you can see on the table, on the green mark, no fault was observed on programs compiled by our toolchain. However, if we introduce a recovery option, it will introduce some kind of bit flip leaks in less under 1%. How is that possible? In this case, you have a multiplication operation, and then the result of those instructions will be compared. If somehow the result is not identical, the system will try to retry both instructions, and it will exit only if both are identical. Because of the nature of the bit flip that always point to the same bit, like on the right side, you can see that source result is always like that on different iterations, then it is possible that actually both multiplication will result on a wrong result. However, it will assume that the comparison will always return the same, which is in this case is SDC, which is a silent data corruption. Some additional insight is that, well, enabling recovery, it is introduced more overhead. In the case of Python, it introduced can up to 4 times compared to the without recovery. And as you can see on the previous slide, this also introduced a bit flip leak. Also, it's still under 1%. And comparatively, this works better on the multi-threaded program because there's less load on the multi-threaded program. And in the case of Scone, of using Scone thread management might help in some cases. In our case, it is Python somehow get faster in our toolchain compared to the native one. There is also EPC, aka enclave page cache limitation on SGX. We try to use Scone simulation mode. It's basically a Scone runtime, but without any SGX features such as integrity tree, encryption, etc. So it's just the Scone framework, and we showed that it gives us quite a significant improvement. Regarding compatibility with other frameworks, we did not test other frameworks such as Graphene SGX to replace Scone. However, it should be possible, but something needs to be changed, maybe in the compilation process or maybe somewhere in the linking process, etc. Conclusion is that we offer the final piece of basic integrity protection by combining SGX and software-based fault tolerance. Our focus is the integrity of the program from both CPU and the memory perspective. The highlight of our toolchain is that it is developer-friendly. It is multi-language compatible, as we shown that it's compatible with at least C, Rust, and Python. It gives us a good performance with up to 37% overhead in normal case and around 80% overhead in the worst case, which is a compute intensive. It also consumes unmodified program, so you don't have to change your program at all, and you can just put your program to compile with our toolchain and then simply run it on the SGX capable machine. On the evaluation, as I mentioned before, on the performance is around 84% for compute intensive, which is in our worst case, multi-threading worst case, and it's between 3% to 37% on the generic multi-threaded programs. We also show that it will detect all the bit flips in our cases, except that if somehow recovery are enabled, then at least some bit flip will be leaked to the program as well. We plan our future work to extend to other architectures such as AMD or maybe some other frameworks such as Graphene, SGX. And we want to optimize the performance. Maybe we can improve it by doing some optimization on the compiler level. And we plan to scale our implementation in the distributed settings and latency sensitive scenario in the real world case. That's from our presentation. If you have any question, do not hesitate to contact me by using my email in the screen. Thank you.